Okay, let's get started. Hey guys, I'm Robin. Today I would like to introduce our graduation project.
Wait. Your face looks too dark. I can't get exposure correct. Oh yeah. Okay, now I can see your face clearly. But now the background looks blown out. I just can't balance the highlight and the shadow.
Let's just switch to another place.
The previous situation is quite common actually. Many real-world scenes contain very bright, direct sunlight to extreme shade. The luminosity range is way beyond which camera can record. Under such circumstances, you can get a satisfying exposure in only one frame. Let me show you some examples. In landscape photography, if you want to keep details in highlight, you will lose details in shadow, and vice versa. The situation is more severe in night imaging because most part of the scene is dark, but also contains some direct light source, such as street lights or advertising light boxes. Fortunately, there already exist some techniques that can cope with wide luminosity range scenes. We call them collectively High Dynamic Range Imaging, for short HDRI. One of these techniques is tone mapping, which takes a group of photos taken on exactly the same scene with different exposures and then merge them into one photo with great detail. But the result sometimes seems to be unnatural. Another method being proposed in 2014 is exposure fusion. The required input is very similar to tone mapping, but it produces a more natural result. Both methods require a group of images, which is not accessible in most occasions, because in order to merge them perfectly, you need a tripod to ensure there's no displacement in any two of the photos. Our project is about HDR imaging in low light conditions, hoping to acquire a well-balanced photo with detail in both highlight and shadow. But different from traditional methods, we did it with only one shot. It sounds crazy, right? How can we do that in only one shot? Ivy, could you explain to the audience?
Okay, let's talk about deep learning first. Deep learning is part of broader family of machine learning, and it's a field of technology that allows machines to learn from data and self-improve by neural network, who mimic the biological structure of the brain. Let me show you an example to explain how deep learning works. If we want computer to recognize that the animal in picture is a rabbit or a sheep, first, we need to prepare a dataset of their pictures, and we set them as input. At the same time, we set the correct answer to each picture as output. Then we can set up a neural network structure, typically a convolutional neural network, that can learn automatically from the dataset. After finished preparation, the computer starts training. The CNN will do feature extraction and classification, and it will get a prediction. Whether the prediction is correct or not, it will be back projected to the neural network. By modifying the weighting of the neurons, an epoch in the training phase is done. After thousands of epochs and massive calculation, we will get a model, the collection of weightings of the neurons. To examine the performance, we input the test image into lab models, and we can get the answer whether the animal is a rabbit or a sheep. The example I just discussed shows the typical deep learning application, but deep learning can do much more than classification. A recent study shows that most image processing algorithms can be learned by a fully convolutional network, another deep learning structure. This theory inspired our project. Our goal is to make a high dynamic range image by just one photo, so we need to train computer to tune the photos in challenging lighting situations into ideal result. First, our dataset contains over 200 groups of pictures. Each picture in the same group has different exposure value, and we preprocess them with exposure fusion. The result is used as the answer, called ground truth. Then we set a -4 EV photo as the input. Our neural network structure is constructed with Python and the most prevailing deep learning toolkit, TensorFlow. So that is a brief introduction to the fundamental of our project. Talk is cheap. Here now is Louis to show our results and make some comparisons.
Finally, the training is over. We got an elegant model. Then we can input some testing image to see how good it performs. Here they are. On the left side are the ground truth image, and their corresponding result images are on the right side. At the first glance, you can hardly tell the difference between the ground truth and our result. Our model recovers color and tone in a very realistic way. It's able to keep most detail in highlight part and shadow. As far as I can say, we have already achieved our goal. But the result is not 100% perfect. If we zoom it, you will notice a slight loss of detail in shadow. The darker parts, that's because these parts in the original imaging is very underexposure and is relatively harder to recover detail than in highlights parts. In conclusion, the current result is satisfying enough, but there do exist more room for improvement. The significance of our project, as Robin has discussed earlier, is that it takes only one picture as input, which is a totally new approach. It makes HDR imaging more accessible. You don't need to shoot a series of photos. You know, the displacement in shooting many photos is almost inevitable and really annoying. And our model takes an underexposed photo. This means the shutter speed can be significantly reduced. In our dataset, the shutter speed of input photo is 16 times faster than a correctly exposed photo. This speed up is crucial in night imaging. Eliminate the possibility of blurring to a great extent. Our technique can be used in any imaging device, especially smartphones. We really look forward to applying our theory to practice.